Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is upward path. The problem difficulty is easy and there are no prerequisites. Let's have a read at the problem. You are given a grid with 2 rows and n columns. The cell at the intersection of ith row and jth column is the grid denoted as I, j. Now each cell of the grid has an initial value that is declared as aij. We can perform the following operation as many times as we want. We'll choose a column and swap the elements, the first and second element in it as many times as we want. And we can do this with any and all of the columns. After the swaps have been made, we start at the cell 1, 1 and we want to reach 2, n. To do this, we can perform either one step to the right or one step to the down. We can do this, that is, we can either change xy to x plus y, y or x, y plus 1. However, we always want to improve. So we cannot move from a cell that has a larger value to a cell that has a smaller value. So it means if we are moving from cell 1 to cell 2, then cell 1 value, let's call it A, has to be less than or equal to cell 2 value, let's say it is B. So the statement says that when we are moving, we cannot move to a smaller cell. Now we need to just find out whether it is possible to go from the leftmost corner to the rightmost column, that is 1, 1 to 2, n. For the input format, we have t test cases and for each test case we have 3 lines. The first line contains the integer n, the second line has n spaced integer. This contains the elements in the first row. Then in the third line we have elements of the second row. Again this has n elements. For the output, we simply have to output yes or no, depending on whether it is possible to move from the leftmost corner, that is 1, 1, to the rightmost corner, that is 2, n. As for the constraints, number of test cases will go from 1 to 10 raised to 5, value of n will go from 2 to 2 into 10 raised to 5, and the value of elements itself will go from 1 to 2 into n. Let's see some sample inputs. So for the first sample input, the grid given to us is of 2 columns. We have 2, 2 in the first column and in the second column we have 3, 1. So let's say we choose this column and swap the elements. This will make the matrix as 2, 2 in the first column and 1, 3. Now once we are starting from this, we can choose to move downwards. Since the elements are same, we can do that. Now we can move to the right. We can do this movement because the cell that we are going to has an element higher than from what we came. Therefore, the answer would be yes. Similarly, in the second sample input, all the elements are same. So yes, definitely we can move. Let's see the third sample input. We have 5, 4 in the first column, 5, 6 in the second column, and 3, 4 in the third column. Now let's say we move from the first column to second column. Since we are starting at 5, although we can swap it, but it does not matter because the second column has the elements that are always greater than or equal to all the elements in the first column. So whether we swap or not, it will not matter. So from first column we move to the second column. But from here it is not possible to move to the third column. Forget about moving to the rightmost corner because there are no elements that are greater than 5. Therefore, the answer is no. Let's see how we can approach the solution. So as we have seen, we can perform the operation of swapping the elements in the column as many times as we want. So let's see, we sort all the columns in ascending order in such a way that C1 will always be less than or equal to C2. So once we have sorted all the elements or all the columns, we will start from 1, 1. Now from this we can do a greedy approach. Since we want to move to a greater number, it is always better that we choose the smaller one first. So let's say we start at 1, 1. This is the smallest element in first column. Now when we move to the second column, we can again check whether the element that will be in this case 1, 2, whether this is more preferable to us or 2 comma 2 is more preferable, right? Remember, these are all sorted, right? The columns are sorted. So we are starting from 1 comma 1 and we want to make sure that we can move to 1 comma 2. If we cannot move to 1 comma 2, we'll check whether we can move to 2 comma 2. If we cannot move to 2 comma 2 also, it means that there is no way to move from this to the other column. So our answer will be immediately no. Now let's say we can move to 1 comma 2. Then again we will check the same in the third column. In any column where we can't move to the first element, we can simply swap it with the second element and check whether we can move there or not. If we can move, it's very good. If we cannot, the answer would be no. Now in this manner, we can reach from left to right? In our column from 1 comma 1, we might be able to reach 1 comma n. But if you remember, our goal is to reach 2 comma n, and we can only perform either right or down operations. So it means that in our path, we have to make at least one down operation. So let's say in this matrix of ours, there will be some x point, right, where we choose to go down. So when we are coming from left till x, what we are doing, we are always traversing in the upper first row. So from the upper first row, we travel till x, we move down, and then we have to travel to right. Now this x column can be anywhere. This can be the start or this can be end. But it is very sure of us that before x, we always travel in the first row. After x, we always travel in the second row. And this can be done greedily, right? As we have seen here, whenever we are changing the column, if we want to make sure that we have to stay in the first row, we'll simply check where we can move. If we can move directly in the first row, we will move. Otherwise, we will swap it so that we can move. If it's not possible, the answer no is always there for us. So with this, it is possible to move from 1 to x. Now the x column, we also need to make sure that the first element is less than or equal to the second element. And that will always be the case. There will always be one element that is less than or equal to the other element. So this movement is possible. Then once we have crossed that we have come down, we need to check whether from this we can move to the right and reach to 2 comma n. Now this is pretty simple. We can just traverse over each I value and check whether it is possible if in that ith column we choose to come down and then move right. But this gives us a O of n square solution because for each value of I we have to check this. We need to optimize this and find if there's any better way that we can do it. Now for the previous value, what we can do is we can simply find a prefix, that is starting from the first column. We can check if we are moving to the second column, which element should we move to, right? And we can come to x because x is any element with and after x is not affected by what we do before. So we can simply have a prefix array that will help us go from the first to the last cell in the first row, right? Similarly, we can also check and try to come from right to left. So if you see in going from left to right, we are trying to choose as smaller elements as possible so that the next element that we can choose will be greater than this. But this will be the opposite if we are coming from right. If we are coming from right, we need to make sure that we are as large as possible so that the previous element that we will choose will be able to come to this cell. So we can do a prefix and a suffix array. Then for each I, we can simply check if the first element, the smaller one, is greater than or equal to the prefix array and the second element is less than or equal to the suffix array. If we find any such I, our answer would be yes, otherwise our answer would be no. And with this, we will get our solution. Let's see how we can implement the solution in C++. So for each test case, we call the function solve. Then we make our grid of 2 rows and n columns. We take all the values and then we sort all the columns in ascending order. Once we have this, we make our prefix array and suffix array. For our prefix array, we choose the smallest element in our column. Then when we move to the next column, we check whether we can move to the first cell or to the second cell. Now, if we can move to the first cell, it would be very good for us. But if we can't, then we will be forced to swap and move to the second cell. But even if both of them are not possible, it means that the element that we have chosen in the current column, there does not exist any element that is greater than this or equal to in the next column. So we can't move forward. Therefore, the answer would be no. Similarly, as we have seen in the approach, when we try to find the suffix, we go from right to left. We try to choose the elements that are as great as possible. But if we cannot choose so, again, the answer would be no. And then to find the answer, we simply traverse over all the indices and check if the smallest element, the first element here, is greater than or equal to our prefix at the previous index, and if it is less than the element to the next index of our suffix. If this satisfies, the answer is a yes. Otherwise, the answer would be no. And as you can see, I have AC in my C++ implementation. Let's see how we can write the solution in Python. Again, for each test case, we call the function solve. Then we take the input of our grid. We swap to make sure that all the columns are sorted in increasing order. So the smaller elements will be in the first row and the larger elements in the second row. Then we find the prefix going from left to right. Then we find a suffix going from right to left that satisfies the condition. And then we try to find which is the index where we can do the down operation, as we have seen in the approach. To do the down operation, the smaller element has to be greater than or equal to the prefix array element at I minus 1, and the second element, the greater element, has to be less than or equal to the suffix element in I plus 1. If there is any I that satisfies this condition, it means that we have a path going from 1 comma 1 to 2 comma n with the operations of right and left. But if that is not the case, our answer would be no. And as you can see, I have AC in my Python implementation too. So I hope you understood the problem, the approach, and how we can implement the solution in both C++ and Python. Have a very good day, and I'll see you in the next video.